A very warm welcome in the class of Mathematics 1. Today our topic is Taylor's theorem and Maclaurin's theorem. Myself Rupak Bhattacharjee, Assistant Professor, Department of Mathematics, GIS College of Engineering. Today in this topic we are going to see how we are relating the concept of function and the concept of infinite series in this particular domain. But before that, we do have some prerequisites for this particular class. They are, first of all, the idea of series, which is already discussed in the previous classes. So along with the concept of series, we need the concept of convergence and divergence and their tests, so that we can get the results related to the convergence or divergence of a given series. As well as we need some basic idea of differentiation, and we must mention that we need the concept of successive differentiation for a given function, because we need nth order differentiation for the topic mentioned over here. Now we are going into the central topic of today's discussion. It is little bit initially a conceptual thing. So first of all, we need to understand the statement and the conditions of the theorem and what are the outcome of the mentioned one. So our initial statement starts like this: if a real valued function f of a real variable x, which is defined in closed interval a to a plus h, be such that first condition, that is our sub condition, fx, f dash x means first order differentiation of fx, up to f n minus 1 x, that means up to n minus 1th differentiation of f with respect to x, all are continuous in the closed interval a to a plus h, and the second sub condition is that if nx, it exists in the open interval a to a plus h, then there exists at least one value of theta where the theta is in between 0 to 1, such that f of a plus h, please mind it here because now we are going to write down the central expression of this particular function. F of a plus h can be expressed as f of a plus h f dash a plus h square by factorial 2 f double dash a plus dot 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 plus h to the power n minus 1 by n minus 1 whole factorial f n minus 1. I can understand that you are able to identify the symmetry plus r n. Now the question is, what is this r n? We will make it clear, but before that I just want to say, if you look at all the terms, there is a symmetry all of us can observe. Now regarding Rn, we can say that where the remainder which remains actually after n terms, first term, second term, third term, so when it is n minus 1, obviously it will be nth term. So the remainder after n terms, this Rn, it is given by, this is very important, Rn is equal to h to the power n by n factorial. Up to this the symmetry is preserved. Then f n, in place of a in all these cases, it will be now a plus theta h. Already what is theta is mentioned, and it is called, it is in the form of Lagrange. So when we are mentioning it by Lagrange's form, that means we are also having one more expression for the same Rn, that Rn can be written as h to the power n 1 minus theta whole to the power n minus 1 by n minus 1 whole factorial fn a plus theta h, and it is in Cauchy's form of remainder. And obviously we know that the range of theta is within 0 to 1. So this is the whole expression. What we can say, that it is nothing but the Taylor's theorem. What is our first part of discussion? So it is our nothing but Taylor's theorem. Now our job is to check what we are going to extract from this Taylor's theorem. First of all, I want to mention that it is nothing but the mean value theorem of nth order. If you can recall the mean value theorem, Cauchy's mean value theorem or Lagrange's mean value theorem, you will be able to identify that it is nothing but the mean value theorem for nth order. Now if we check the expression of Rn, then it is very simple for us to prove that if n tends to infinity, Rn tends to 0, and we can get the Taylor's infinite expansion. Up to this it was finite, but when we are making n tends to infinity, then Taylor's infinite expansion is achieved. and this Taylor's infinite expansion becomes f of a plus h is equal to fa plus h f dash a plus h square by factorial to f double dash a dot 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 h to the power n minus 1 by n minus 1 whole factorial f n minus 1 a plus dot 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 means it is now becomes an infinite expansion. Okay, so this is the whole thing all about the Taylor's theorem. Now if this Taylor's theorem is there in our mind, and if we make a suitable change in this form, that in this particular Taylor's infinite expansion, if we put, means if we insert actually x is equal a is equal to 0 and h is equal to x, then we get f of a plus h will become f of 0 plus x, so it is simply f of x is equal to fa will become f0 plus h f dash a will become x f dash 0 plus x square by factorial 2 f double dash 0 plus dot 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 and so on. And also here we have to mention that provided Rn, that means the remainder term x to the power n by n factorial f n theta x, it is in Lagrange's form. Just if we put this particular requirement a equal to 0 and h equal to x in Lagrange's form, then we will get this one. And similarly we can write Rn is equal to x to the power n 1 minus theta whole to the power n minus 1 by n minus 1 factorial, it is in Cauchy's form. And all of them will be tending to 0 as n tends to infinity. Otherwise we can't continue by writing this. Now the question is, putting this or making this suitable change, the Taylor series becomes a special form of an infinite series which is having the name Maclaurin series. So it is nothing but Maclaurin series, or sometimes it is termed as Maclaurin's theorem, and this is for obviously infinite expansion of fx. It is nothing but for infinite expansion of fx provided these conditions are maintained. So this is the fundamental results or statements, what you can say, for Taylor's theorem and Maclaurin's theorem. Now in the next part of this class, we are going to see that how we are going to apply these theorems for getting the solution of some problems. So our problem is now first, suppose the question is show that x plus h whole to the power 3 by 2 is equal to x to the power 3 by 2 plus 3 by 2 into x to the power half into h plus 3 by 2 into 1 by 2 into h square by factorial 2 1 by root over x plus theta h, where the range of theta is within 0 to 1, and this question is also associated with that find theta, means value of theta when x is equal to 0. Now we can start solving the problem and we can find out the solution also, but the requirement is that how to identify that which method we are going to apply for proving these problems. So first of all, if we see that the result what we have to prove, it looks like that we are differentiating something gradually, and after a certain time, that means after a finite time, we are stopping our problem or the result where the last expression is not exactly similar with the previous expressions or the similar pattern with the previous terms. So it may be treated as the remainder term. So in this manner, we can get a clue from this question that we may have to use Taylor's theorem or Lagrange's or Maclaurin's theorem for these types of problems. So let us start how to find out the solution. So let fx is equal to x to the power 3 by 2. Because we are seeing it is x plus h to the power 3 by 2, the first term is x to the power 3 by 2. So these are the nothing but the clues through which we can assume that we may take that fx equal to x to the power 3 by 2. So f dash x will be 3 by 2 into x to the power half. F double dash x will be 3 by 2 into 1 by 2 into x to the power minus half. And after that we don't require it because it is stopped after second order differentiation. Now if we think about the nth order general mean value theorem, and if we are extracting from it the second order mean value theorem, so you can write that now second order mean value theorem gives us f of x plus h is equal to fx plus h f dash x plus h square by factorial 2 f double dash x. But as we are stopping it at the second order MVT, so we have to make after this the remainder term. So it will be h square by factorial 2 f double dash x plus theta h, x plus theta h within the range of theta lying between 0 to 1. And now according to our assumption, we can get f of x plus h will be x plus h to the power 3 by 2. F of x is x to the power 3 by 2 plus h. Now f dash x is already calculated. So 3 by 2 x to the power half plus h square by factorial 2. F double dash x is calculated, but we need f double dash x plus theta h. So it will be 3 by 2 into 1 by 2 into x plus theta h whole to the power minus half. Now simplifying, we can write it as x to the power 3 by 2 plus 3 by 2 x to the power half into h plus 3 by 2 into 1 by 2 into h square by factorial 2, then 1 by x to the power theta h to the power half, which is nothing but root over x plus theta h, because it is to the power half. So already our first part is done. Now for the second part of the question, that means we have to find out the value of theta when x equal to 0. So we can put x equal to 0 in this expression. We get h to the power 3 by 2 is equal to, this is 0, this is 0, this will be 3 by 2, then 2, then 2, so 2 to 4 to 8, so it will be 3 by 8 h square 1 by root over theta h. And after simplifying this, we will easily get that the value of theta will be 9 by 64 h square, and it is root over h, so h to the power half. So h to the power half, it will be up h to the power minus half, so 2 minus half, it will be 3 by 2. H will be cancelled out. This is theta to the power half. If it is go here, it will be theta to the power half. So theta will be 3 by 8 whole square. So 3 into 3, 9, and 8 into 8, it is 64. So in this way, we will get the answer of our required problem. So this is a very beautiful application of Taylor's theorem, what we can claim. Now we will move for another problem. This problem asks us directly that apply Maclaurin's theorem on fx, where fx is given as 1 plus x whole to the power 4. To deduce that, one plus x whole to the power 4 is equal to 1 plus 4x plus 6x square plus 4x cube plus x to the power 4. Before solving this problem, I want to give a caution to all our listeners that we have to concentrate on the question, that we have to apply Maclaurin's theorem on this given function to deduce this. It is not that we can find out the result of 1 plus x to the power 4 is equal to 1 plus 4x plus 6x square plus 4x cube plus x to the power 4 directly by multiplying 1 plus x whole square plus 1 plus x whole square, or by any other means. We have to follow the instruction that applying Maclaurin's theorem on the given function fx equal to 1 plus x to the power 4, we have to find it out. So this is one very important caution what we have to keep in our mind while performing these types of problem. So now the problem can be done easily. Fx is equal to 1 plus x whole to the power 4, it is given. From this we can find out f dash x, f double dash x, f triple dash x. Okay, and after finding all these, and obviously according to the requirement we will go for also f4x, and after finding all these we can put the value of x is equal to 0 according to the requirement of Maclaurin'S theorem, and we will get the corresponding values for this. Now the Maclaurin'S theorem is going to be written, the statement, with suppose Lagrange's form of remainder, and then we will use these expressions with the value of x equal to 0 putting over there, and simplify the Maclaurin's theorem for this particular function. We will get our desired result as the expression of 1 plus x whole to the power 4. So this is kept to you to complete the process and find out the expression of the result as desired by us or by the question. Now you can find out some problems like this. I am just going to give you another problem that we can also find out the problems like this, that if minus 1 less than x less than 1 is given, and 1 plus x whole to the power 1 by 3 is equal to 1 plus 1 by 3 into x minus 1 by 9 x square plus 5 by 81 x cube and so on, and after that it is given as R5. Whenever it will be R5, you have to decide that here n is equal to 5, so all these expressions will be up to n equal to 4, and R5 is also given is equal to x to the power 5, means you have to show it by the application of Taylor series, and depending on the expression asked in the question you have to decide that what type of remainder you are going to choose for proving this particular requirement. This is only the important part of these types of questions, that what type of remainder you are going to choose. In the previous problem we have to choose Lagrange's form of remainder, but here this particular theta gives us the clue that we have to go for Cauchy's form of remainder. Obviously I am not restricting any one of you to solve the problem by only one way. You can think and you can try the problems to solve by various approaches. So this is all about, not all about, this is the initiation of about Taylor's theorem and Maclaurin's theorem. So finally I want to mention that we are using the particular reference for preparing this lecture, and these are some assignments. Obviously these are not at all the whole list for you to solve it out. So thank you all. Happy listening, happy learning.